we learned a lot about the nurse managing wavelength therapy and a lot of good stuff. Now I would like to change your pace by going to the training. Actually, here we apply and you are expected to receive the very few slides motion. Now I'm going to show you why we need this motion. So I think I don't need to recall you over the past because optical telecommunication has a lot of applications. Because of this universal usage of the optical telecommunication, many silicon photonic chips developed. Due to unique characteristic of optic or light, which is traveling straight, optical alignment between different chips are needed. So also I have to mention that when we talk about the silicon photonic chips, and silicon photonic chips are made of the passive and active component, so we need to have the alignment. Currently, in order to provide the alignment, we use such a bulky machine, which we call it pick and place, and to align the active chip with the passive chip. However, we need optical aligner with some specific feature, like a low power and scalable, and most important, we should be able to use such a technology during the package, making the chip and align do everything at the same time. So, because of that, microelectromechanical technology or MEMS can help us to reach such a solution. So basically, this is my outline. I'm going to start with a short introduction on the current status of the MEMS aligner, and then I'm going to introduce for vertical electrostatic MEMS aligner with having optical waveguide surface, and then I'm going to show you some results and finally finish this conclusion. So at the micro scale, we can create the in-plane and out-of-plane motion with different actuation mechanisms: electrothermal, electromagnetic, electrostatic, and piezoelectric. Indeed, each of these techniques has own advantages as well as disadvantages. However, when we talk about the out-of-plane motion, piezoelectric actuation mechanism shows great potential. In this, when we in using the piezoelectric actuation, we have a normally thin layer of device layer, which normally made of polysilicon, and thickness of the polysilicon cannot exceed 6 few micrometers. So, for example, in this case, we have polysilicon as a device layer. On top of that, we have a PCT, and once we apply the voltage, we have a deformation out of plane. But once we talk about the optic and optical waveguide, is it has a high residual stress. So since it has a high residual stress, in terms of the fabrication, we are not able to make the optical waveguide on top of the polysilicon, since polysilicon is very thin. So then I'm going to, in this study, we came up with the new actuation mechanism. Is electrostatic, and and we can use a very thick device layer for creating. So here you see the schematic of this micro. I'm using the aligner and actuator, but most of the terms are external. So here you see the schematic of the aligner. This aligner is anchored from 2 points and also has a low stiffness beam along the y-axis. At the center of this aligner, I have a regular cold drive. Here I have to mention that this cold drive and movable finger are located at the same plane. So once I apply the voltage to this drive, I have an electrostatic force, but since I have a lowest stiffness peak along the y-axis, I'm creating a small rotation. So this rotation at the end of the actuator shows the vertical displacement. So then the place that I have optical interconnection, I'm having the vertical displacement. Here in this schematic, yellow color represents optical waveguide. As you see, the optical waveguide are routed on the entire suspended device. I have an input waveguide, which I can apply the optical signal, and I have the output grading color, which can measure the received optical signal. So in order to fabricate this device, we use a fabrication process flow, which was developed by our industry partners, Electronics, startup based Montreal. So here the device layer is 59 micrometer, as you can see here, silicon, relatively thick when we compare it with silicon. And also I have a silicon nitride waveguide, which is clouded with silicon dioxide on top and bottom. So basically I have a silicon which is working as an actuator for creating the electrostatic, and also I have a light. So this is the picture of the device. The length of the prototype is 1.4 millimeter in 26. So let's go to some result. First, we investigate the effect of misalignment in the optical system. For doing that, we used the console and we did the 2D simulation. How the 2D simulation is not super accurate, but still it gives us some expectation. For investigating the misalignment effect, here I modeled the silicon nitride waveguide. I have one of them is fixed and other one is movable, which is can shift along the y-axis. As we expected, when fixed and movable waveguides are perfectly matched, we are able to transfer the maximum power from input port to the output port, which is you can see. However, once we introduce the around 500 nanometer misalignment between the fixed and movable waveguide, the transfer power reduces 80%. So although we have a 500 nanometer misalignment, but 80% power can reduce. So in order to measure the displacement, because we are working with a very tiny motion, we use the confocal microscope. Here in this plot, you see the mechanical profile of the actuator at the vicinity of the optical interconnection. Here is my fixed waveguide, and the other one shows my movable waveguide. You see that the movable waveguide is down around 350 nanometer when we compare it with the fixed waveguide. This is due to two things: first, gravity, and the device is lower, and also because of the residual stress of the optical waveguide, as I mentioned earlier. So once we apply the 90 volt to the full drive, what's happening is that the movable waveguide elevated and the movable waveguide is staying at the same level as fixed. So basically what I can say here is that by applying the DC voltage of around 90 volts, we can remove these 350 nanometer misalignment. So now let me show you the optical characterization. In order to characterize this liner optically. We use the tunable laser. We apply optical waveguide in input grading, and also we use the photodetector, and we measure the receive power at the output grading coupler. So, and the results are presented in this plot. X-axis shows wavelength, and Y-axis shows the amount of power that is transferred from the input grading coupler to the output grading coupler. In two cases. The first cases, which is shown by a red color, is when we didn't apply any voltage to the liner, you see. And once we apply 90 volts, then we are basically removing the misalignment, and insertion loss can reduce 3 dB over the wide range. Of course, I have to mention that if you look at this power, you're going to tell me that's not a very perfect power still, but I have to mention I have a 4 micron adapter. So by having the in-plane actuator, which is very simple, we can use the parallel plate capacitor, we can close this gap, then this loss can be significantly reduced. So here I have a vertical displacement, which is measured by a microscope for different voltages. Blue curve shows simulation, and one in the console, and the red one shows measurement. The maximum discrepancy between simulation and measurement is around 15%. The other one shows the other plot shows the x-axis again is the actuation voltage, and the y-axis the transmission for different voltages. As you can see, after certain level of the voltage, you kind of reach to the constant value, because we kind of remove that initial misalignment between two waveguides. So let's conclude this part. Here we propose a novel actuation mechanism based electrostatic. Because of this novel actuation mechanism, we are able to use the thick device layer. Thanks to using the thick device layer, we can integrate the optical waveguide in our system. I experimentally shown that by applying the 90 volts, we are able to remove that 350 nanometer initial misalignment. And this removing initial misalignment actually can reduce the insertion loss 3 dB over the wire range. So, and the last point is that in this study, basically we're trying to show that integrating the MEMS actuator with optical waveguide, we can reach better optical performance. So at the end, I would like to thank our funding agency, and also I would like to thank you for your attention.